By default, a tree is fully grown, i.e. each leaf contains only one observation. What is the training error for such trees? Whether we are in regression with a quadratic loss, for example, or in classification with a 0-1 loss, the error of such a tree on the training set is 0. Indeed, since each leaf contains exactly one observation, the mean in regression or the majority vote in classification is exactly the label of the observation in question. The difference between the prediction and the label of the observation is therefore 0 and is solved for each observation. The risk of such a tree on the training set is therefore 0. The tree builds predictions that are therefore perfect on the training set. Unfortunately, even if the training risk is 0, the tree is not perfect. It is unlikely that the error for this tree on a new set of observations, which were not used to build the tree, is 0. This difference between a very low training error and a high test error, calculated on a new data set, is called overfitting. We say that the tree overfits if its error, calculated on the test set, is large compared to the error on the training set. We must therefore try to limit this phenomenon since we want to obtain a low test error. Indeed, only the test error reflects the predictive performance of the estimator applied to new data. The error on the training set is only an indicator allowing to build methods more or less adapted to the training data. Overfitting thus appears for fully developed decision trees. A general technique to reduce overfitting is to limit the complexity of the method considered. The complexity of a tree can be measured by the number of splits or the depth. Two approaches exist to limit the complexity of the tree, thus reducing overfitting. The first one, more straightforward, consists in adjusting the hyperparameters of the method to constrain the structure of the tree. This can be done via the hyperparameters corresponding to the minimum number of observations in each leaf, the minimum number of observations to cut, or the maximum depth of the tree. The generated trees are shallower, contain more observations per leaf, and are therefore less likely to overfit. Another more common approach is pruning. Such an approach is decomposed in two steps. In the first step, a fully developed tree is built, and in the second step, this tree is pruned. Some branches of the tree are removed in order to obtain a simpler tree, which then have better generalization capabilities, i.e. a better performance on a test set. These two approaches may seem similar. Nevertheless, pruning is to be preferred to hyperparameter optimization, as the former approach offers more flexibility in the final structure of the tree. Note that approaches that stop the construction of the tree when the impurity reduction computed on the training set is too low do not work in all generality. To see this, let us consider such a construction. Imagine that the construction of such a tree stops because the impurity reduction is too low within a cell. Because of interaction phenomena, it is quite possible that the impurity reduction is very low at a given level, but increases at the next level. Indeed, in the presence of interactions, cutting according to one variable may not be informative, but cutting according to two variables successively will be very informative. In such cases, stopping the construction of the tree when the decrease in impurity is small enough can be detrimental to the overall predictive performance of the tree. For this reason, one should avoid stopping the construction of the tree on a criterion based on the impurity reduction.